Hello everyone, my name is Daniel Tooker, and I'm here with an independent research topic that I'm presenting for Electronic Communications 2 at Eastern New Mexico University, EET 457. I'm going to try to keep this pretty short, so it's going to be more of a crash course in HDMI and TMDS. And the topics I'll be covering today are going to be what HDMI is, and I don't want to insult anyone because most of you probably have used HDMI in your own configurations at home. It's a pretty common standard now, but I do want to kind of just do a quick introduction to it for those of you that haven't, and then to facilitate some of the concepts I'll be presenting during the slides. So I'll be going over a quick introduction to HDMI, and then after that I'm going to get into the information types and channels that pipe data through on an HDMI cable. And then I'm going to get into the cable types and construction methods, so kind of break down the transmission line there. And then I'm going to get into the limitations of that transmission line, so where the standard and where the implementation of the standard kind of falls short. And then I'm going to get into some of the example test equipment that might be used to test HDMI cables, transmitters, and receivers. And because HDMI is largely based on transition minimized differential signaling, or TMDS, I'm going to have to get into what that is and how that works, because that's the bulk of the data throughput on an HDMI cable is TMDS. So we'll get into what that type of signaling is, and I'll show you a transmission and receiving block diagram using TMDS. And then I'm going to get into the encoding. The TMDS encoding on the more modern HDMI standards uses scrambling with linear feedback shift registers and a generating polynomial. This produces stability and helps with error detection and correction and that sort of thing. And they were able to actually use that generating polynomial and the concept of linear feedback shift registers to greatly enhance the data throughput of an HDMI cable. And then I'm going to get into some example implementations of HDMI with electronic components and their applications. So without further ado, let me just introduce you to HDMI. Most of you probably already used it before, like I said, but it is called the High Definition Multimedia Interface. It was first launched in 2002 and has seen many revisions since then. It is the most currently released specification is 2.1. Now that goes up to a data throughput of 48 gigabits per second on the TMDS quad pair. So there's not many devices yet that are leveraging this newest standard. Most devices currently on the market are revision 2.0. It is HDMI is a proprietary audio-video interface, although it does pipe more than just audio and video through on some of its channels. And it is used to transmit uncompressed video data and compressed or uncompressed digital audio data. And HDMI is a digital replacement for earlier analog video standards. It is built around the EIA CEA 861 multimedia standards. It's not too important that you know what this is, but it does come up if you ever end up working in communications industry or high-speed information exchange, some sort of job like that. You will probably encounter this standard. It defines video formats and the waveforms for those video formats. It defines the transport of compressed and uncompressed linear pulse code modulated audio and defines the transport of auxiliary data. It also implements the VESA, Extended Display Identification Data, which is a mechanism that devices can exchange information to each other and have awareness of each other's capabilities, so that a video or audio signal that the display isn't capable of reproducing won't actually be sent something it can't do anything with. That's what HDMI cable looks like, and you all probably already know that. What you might not have known is to work with these as a manufacturer and implement HDMI in a compliant way, you have to become a certified HDMI adopter. And so this involves paying licensing fees and royalties on per units manufactured, and of course sending a sample size of your production off for compliance testing. And so this applies to cables, this applies to the transmitters and the receivers. And having a program in place that regulates the compliance of HDMI, furthers the technology. So there's kind of a money flow there for that. And of course, it helps consumers ensure that they're getting what they pay for. And the current standard allows the currently most recently released set of HDMI specifications 2.1 allows for resolutions of up to 10K, 8K, and 10K at 60 hertz, HDR, and a lot of other optional features that manufacturers can implement if they choose to do so. And of course, with the evolution of the different standards from HDMI, we have been seeing constant increases in the data throughput. Back at 1.4 was 10.2 gigabits per second. The most widely and currently available standard that is implemented in devices on the market right now is the 18 gigabits per second HDMI 2.0. And right around the corner, we're going to start seeing some devices with really high-speed chipsets, system-on-a-chips, FPGAs, and that sort of thing that can pipe out data at 48 gigabits per second with HDMI 2.1. All right, so you probably have seen the connectors, but you may or may not have known just how many pairs of wires are being routed through that HDMI cable and what the purposes of those different channels are. And I'm going to break these down a few more slides deeper down here in the presentation. So just hang in there for that, but I just kind of wanted to show you the inside of the cable before I start talking about what type of information is transmitted over HDMI. So you can see there's a lot going down there, and like I said, I'll break that down. I just wanted to show you that really quickly here before talking about the types of data piped through with HDMI. Number one is the pixel color data. That's basically your video data. And then you're going to have your audio data. All of those are going to be in a digital format. To my knowledge, HDMI does not transmit any analog sound whatsoever, but there are many, many digital formats, pulse code modulation, and a bunch of proprietary formats like DTS and Dolby, the two leading competitors in this digital audio delivery format. They also produce the sound for theaters as well as home theaters and internet streaming services and that sort of thing. And the third type of data piped through HDMI is going to be your timing information and your auxiliary data, such as consumer electronics control. So those are the three types of data that are piped through on an HDMI cable. And these are the 5 channels that it uses to accomplish that. And I'm going to break down each one of these channels briefly here. So TMDS, and perhaps the most important one, where the largest amount of data is being piped through transition minimized differential signaling. This interleaves audio, video, and auxiliary data, and it has different periods where it does this with. You can think about it like TDM or time division multiplexing, because during certain periods, video data packets are being piped through, and during other periods, audio data packets are being piped through and control information as well. So it's kind of dividing up the time and sending through data for each of those types of things at different times during a given sequence. And that's their schema for how to get all that data through on just 4 TMDS lines. DDC. So this is a display data channel. It is a simple communication channel based on I²C. And it's basically to allow for some awareness from the display and the source for compatibility. It's basically a table of hex codes that'll get exchanged over serial clock and serial data lines so that the devices are aware of each other's capabilities. Audio return channel is so that audio can be sent down back in the opposite direction. Instead of audio coming from the generation source to the sink, like the display, it can come from the display to the source. So if you have an AVR in your home theater setup, you can actually use those smart apps on your TV and have the sound piped back from your TV to the AVR. HEC is an optional feature. It's called the HDMI Ethernet channel. Uses a single wire with a ground and has 100 megabits per second bidirectional link. CEC allows for the user to control up to 10 enabled devices connected through HDMI. So these are the 5 channels present in an HDMI cable. Some of these are optional. Not every cable may have a dedicated wire for the CEC, HEC, or audio return channel. That does depend on the manufacturer and the revision of HDMI to which they are manufacturing for. Now, one of these I do want to break down a little bit further here for you because it is important in the amount of data that's being piped through, the concept of differential signaling here. What differential signaling is, it's pretty simple. Compared to your single-ended transmissions, as you see in the diagram at the right, you've got your logic level low, high, and the transition from low to high, and the transition from high to low over and over and over again, representing your zeros and ones. Differential signaling has two pairs that share a ground, and what they do is they're equal and opposite of each other at all times. And it kind of seems pointless at first glance, but there are a lot of advantages with sending your ones and zeros this way. One of the primary advantages is that they cancel their own noise because the waveforms are equal and opposite of each other, and those wires in cables and on PCBs for traces, they're routed close to each other. In fact, in cables, they're a twisted pair. So they cancel each other's EMI, and they are also less susceptible to external EMI. They also allow for lower voltages in systems as well. And there's a little noise diagram on how these differential pairs work and how they cancel noise. Further on in the presentation, I will do a comparison to single-ended signals and these differential signals here, and I'll make that picture a little bit bigger and easier for you to see. But just know that differential signaling allows for a lot more data throughput because of their almost indifference to noise. They're very, very good about not only canceling their own EMI, but also being less susceptible to external EMI. Okay, so back to the cable here. I promised I'd break this down, and let's get into that. The first thing I want to point out is that with a good cable design and a good manufacturer, they are triple shielded. And not every manufacturer makes these cables out of the same high-quality materials. This one here, I think that we're seeing, is a silver tin conductors with foil, and it's got 3 layers of foil. It's got your mesh shielding right before the PVC jacket for the whole cable, and then it's got a foil layer inside of that, and each of your TMDS pairs have gold foil on them, and those are called your TMDS channels. And again, what I want to bring up that little noise diagram here, because not only do you have these pairs, you're seeing the brown and white, red and white, green and white, blue and white, that not only do they have the advantages of being a differential pair for noise cancellation, but they've also got that shielding and lots of it. So this cable is designed for a lot of data throughput with good signal integrity. So these are an unbalanced line. We've talked about these in our higher level communication courses there at ENMU. They're a twisted pair. One of these pairs here on screen are obviously twisted, but just know that the ones inside the gold foil are also twisted pairs. They just happen to also have a ground in there. They have that dedicated ground, and of course they have their own foil. Now this is TMDS channel 0, and again I just wanted to reiterate that this is a transition minimized differential signal coming out of these pairs. So as you can see right there, each one of these gold foil pairs are producing a signal just like this. For all the data they pipe through, it is this type of signal coming out. So that's TMDS channel 0, 1, and 2. And if you haven't guessed already, during the period of time when video data is being transmitted, channel 0, 1, and 2 are transmitting your RGB, red, green, and blue pixel values. And then, of course, during the data island periods for the sequence of HDMI, the model in which it works, it's also going to pipe audio data through there. It has that 4th TMDS clock channel. Other uses of some of these wires here, again, some of these are optional, but I'm going to go ahead and label these as if a manufacturer decided to fully implement every feature. You've got your 5 volts and your CEC, which is the Consumer Electronics Control. Your 5 volts is used to detect when the cable is plugged into another device. That is called the hot plug detect. So the HDMI cable actually does send out a 5 volts DC constant signal level, and then one of these other wires is a return for that level. And what happens with that is when you get that return detected, that means the cable's been plugged in, and it can begin exchanging the display identification data on the serial clock and serial data lanes, which is an I2C DDC channel. And then I'll bring those down here so we don't get too crowded there. That's your DDC, Ethernet, and CEC return ground. That's your hot plug detect. That was the one I was telling you about, that the 5 volts is returned on. And then, of course, that purple one might be the HDMI Ethernet channel. Now, it is worth noting that no one manufacturer of cable or manufacturer who terminates these cables with connectors, they're not consistent with color coding. So other than the gold foil pairs there, I could have easily mixed up the color coding there, and any one of those could be flipped around from one manufacturer to another. But I did my best to probably pick what was likely. So that's what you've got on your different channels coming through. I'm going to move that over and just show you to remind you which type of data is coming out where. So on your channel 0, 1, and 2, you've got your interleaved video and audio coming out of those. Out of your serial clock and data lines, that's the DDC channel, you've got your display identification data, and then of course you got the clock channel. Now I've got that asterisk there on the clock channel because in the newest revision they have found a lot of freed up overhead on that clock channel and have found ways to pipe even more data in through that clock channel. So that 4th TMDS pair has been maximized in the newest standards so that it's not just using clock timing information, but it's also transmitting some other type of information. So this right here is an example of some test equipment for HDMI cables, transmitters, and receivers. This device can be used in line. It's basically a handheld scanner, and that is the exact one you see there in the hard case. And what that does is you can plug up to an HDMI cable and detect some of the data and rates of the types of data and the rates for those data that are coming through, and identify those and see if they're coming through like they're supposed to be. So this would be very handy for an installer or a troubleshooter who works on these types of systems in a commercial environment, or maybe even as a home installer for home theaters and stuff like that. So like I said, the various information types of an HDMI signal can be seen in the photo. This is a Muridio Fresco pair scanner, and one thing not shown, however, on this scanner is the EDID. I did not dig through the documentation for these, so there may be a screen where you can pull up the EDID, but the EDID is the extended display identification data. This is where the source and the sink, or the device that's generating the video signal, and the device such as the TV that is, or projector that is displaying it, is called a sink. Those devices can exchange information to each other about their capabilities so that the right type of signal is being sent through. And that's just a table of hex codes, basically flags identifying what types of audio it's capable of reproducing, what its maximum resolution and frame rate that it's capable of reproducing, whether or not it's HDR compatible, and whether or not it is HDCP compliant. I'll get into HDCP at the very end of this slideshow. It's kind of outside of the scope of this presentation. All right, so HDMI cable limitations. So the limitations of the transmission line. So one of my favorite manufacturers of HDMI cables, because I've been toying around with this stuff for many years, is a company called Blue Jeans Cable. I've got them down in the references here because they make very high quality cable. They work with Belden to get perfectly ideally matched lengths of twisted pairs for those TMDS channels, and there's no signal skew because of that. Also a little bit outside of the scope of this, but one thing they did say about HDMI is that it's a fragile interface, not least of which because the difficulties of manufacturing twisted pairs, fine tolerances, and the extraordinary bandwidth requirements of the HDMI signal. So the primary limiting factor for HDMI cables is cable length. 50 foot is generally considered to be the maximum reliable length, but what I have found in practice is that that is actually much shorter. As soon as you start pushing up that resolution and frame rate, if you're doing above 1080p, or if you're getting up in the 4K territory at 60 hertz, you're going to have to use the shortest cable possible to avoid bitrate error. I'm going to talk about bitrate error here in just a moment. Several methodologies such as improved cable design and characteristics and active repeaters, error correction, and fiber optic encoders and decoders, which basically replace the cable altogether, have been employed to reduce the error rate of longer cable runs. The fiber optic replacement for HDMI cables is a very neat topic. They basically encode at the transmit side and decode at the receiver side, and they replace the copper or silver tinned or whatever you have, conductor type cable. Whatever you have there, it's replaced entirely by fiber optic. And as long as the encoders and decoders are fast enough for the data throughput you're trying to achieve, it is an excellent solution, and you can make remarkably long runs with practically zero bitrate error. But that's outside of the scope of this. I just want to talk about the actual cables that are most commonly used in everyday applications in the home and retail environment. Okay, so like I said, cable length is the primary limiting factor. There are no numbers on these charts because it varies greatly from one cable manufacturer to another. I could take two cables that are supposedly compliant with the same HDMI standard, and it is anyone's guess whether or not they're actually certified. There's a lot of people cheating out there, and they're using the HDMI logo even though they're not a certified HDMI adopter, and they have not sent out their hardware or their cables for compliance testing. So it's pretty difficult without some high-end test equipment and a lot of time to dump into it to find out if a cable really should have been certified or if it ever was certified in the first place. But in general, even with the high-quality cables, the longer the length, the more degraded the picture quality will become. Now, notice this isn't a linear drop-off in picture quality. There's a bit of a cliff there. And that's an interesting topic all on its own. I'll try to get into a little bit more of that, but not a whole lot. So what you get is an increased error rate as the cable length increases. And it's pretty slow at first and steady until it approaches that cliff right there. And the bit error rate, or the BER, which we've also discussed in our course, dramatically increases the closer you approach that theoretical cliff, which we said most people agree upon is about 50 feet. But in reality, with higher frame rates and resolutions, that is going to be a lot less than 50 feet. You're going to want to stick to 6 meters or less, probably 3 to 6 foot cable. If you can keep it under that, you're doing yourself a favor, because you won't have to mess with trouble displaying your content or your audio. So what those differential pairs look like on an oscilloscope is often referred to as an eye pattern. It's what TMDS signals look like. Also, it is what low voltage differential signals look like, another type of differential signaling. So you've got your many traces of the ones and zeros overlapping each other that resemble an eye shape. So as the signal further degrades, or as the amplitude is lost over a really long run, you'll get what's called a closed eye, and there's digital signal processing techniques to open that eye back up and clean up that signal and retransmit it. So those are called an active repeater, or if it's not a repeater, it might just be on the receiving end to help clean up that signal and try to recover it. This is a block diagram for a TMDS transmitter and receiver here. In this case, it's showing you 8-bit red, green, and blue video data being piped through, but keep in mind that HDMI also utilizes these channels to pipe through audio data in the video island, or in the data island periods, which are the periods outside of the active video area. But you get the idea there. The triangles on the left are a buffer. One is just directly connected. One is an inverted buffer. And so those signal levels are always equal and opposite to each other. And on the other end, the triangles on the right, you just have op amps, which are canceling out that noise and returning those differential pairs back into a single pair. And the fourth one, the white triangles at the bottom, are the same thing. It just happens to be the clock channel. Speaking of TMDS, I talked about this a little bit at the beginning. We have linear feedback shift registers. They're used for each of the TMDS data channels on the encoding or source side, and one linear feedback shift register is used for each of the TMDS data channels for decoding on the sync side. Now, each bit in the diagram below is represented as a D flip-flop, respectively from the least significant bit on the left to the most significant bit on the right. And that's essentially just a shift register, a bunch of D flip-flops. And there you can see the generating polynomial for TMDS transmission in an HDMI system. And now this did come out of the HDMI specification version 2.0, so this is for educational use only. A little disclaimer I've got to throw up in there. You do have to be an adopter to even get the specification for HDMI. And so here's another way to view that data stream coming out of those differential pairs. The dark green you see there is what's transporting the pixel color data or the active video data, and that dark blue surrounded by the two red bars there is where you're seeing the auxiliary data being transported in the audio. And it looks like, man, that's only a little bit of space for audio compared to a lot of space for video, but in reality you do need a lot more data for video than you do for audio. And here's how they accomplish that. So here's another way to visualize that data that's coming through. And what you've got is a couple of porches. What they used to call in the old CRT world is the front porch, back porch, and your blanking periods or your blanking intervals. Those are the areas above the screen and to the left of the screen where data other than just the active video lines can be transmitted, and that's where you're able to get for every single frame. So one frame, which in a 60 frames per second setup, this amount of data is being transmitted 60 frames per second. So this data on screen here 60 times in 1 second. That's plenty of room for audio. So the overall frequency at which the frame is presented to the sync device is fast enough that there's plenty of room for high definition audio packets to be delivered in between the delivery of pixel color information. I told you I would talk a little bit more about differential signaling here, and I wanted to compare the effects of noise on a single-ended signal versus a differential signal. On the left, you can see that single-ended signal there with logic high, logic low, and you can see noise and how those two combine, and it dramatically affects a single-ended signal. Especially in high speed, the faster it is, the shorter those periods are going to be, and the more catastrophic the effects of noise are. But as you can see in the diagram here with differential signaling, the noise effects are canceled out due to the nature of the op amp that's used to recover the differential signal at the other end. So you have a buffer and then an inverting buffer, or a NOT gate, if you will, that is causing those two pairs to always be equal and opposite of each other. And then at the other end, you've got that op amp that is amazing at canceling out the noise for recovering that signal at the other end. And there's that diagram again, just blowing up a little bit. It's interesting here that it does point out these differential signals are used in low voltage differential signals, ECL, PECL, RS422, and so on. But they are used here in transition minimized differential signaling, and just like the name implies, the transitions from high to low and low to high are minimized in an attempt to get the highest data throughput possible on these HDMI cables. The ones I said that I were using are HDMI 2.0, and they're 18 gigabits per second. And that is quite a bit of data throughput. So the transition time for these signals to go high to low have to be as absolutely minimized as possible in order to achieve such a data throughput. And without further ado, we're getting close to the end of the presentation here. Just wanted to show how HDMI and a TMDS system might be implemented on a circuit card or in a new design. This one here you're seeing is older. It is an evaluation board from DigiKey, which uses a Texas Instruments TFP 410, which was using the DVI 1.0 standard, which is nearly identical to the earliest version of HDMI. It is a transmitter. And so this chip is a little bit dated, but it is a good example of TMDS baked onto an ASIC, or an application-specific integrated circuit, not reprogrammable at the field level. It's just really cheap and can get the job done at the speeds required. But this one in particular only supported video, and because this was at the time that HDMI was still a brand new specification. So here's a little bit of a newer device. This one here you might find in the receiving end of, actually inside the TV is what's receiving your video signal and just converting it into RGB values plus audio. And this one I think is probably multiplexed. This is a great company, Analog Devices. Despite the name of the company, this is not an analog device in any way, shape, or form. It is purely digital. but it is the ADV7623. It's a multiplexed receiver, and what this does is decode the TMDS transmission lines and converts that into raw, unencrypted RGB values with a refresh rate for your screen. And of course, it separates out those audio packets and recombines those back into a continuous audio stream. Now, there's a block diagram on here. I don't expect you to be able to see that. It's probably too small on the screen you're viewing it on. But one thing I did want to point out on the block diagram, that in the block diagram came from the data sheet, but I wanted to point out one concept about HDMI that I haven't mentioned yet, is the HDCP, and that is the encryption that is used to ensure people cannot rip off content, or at least not easily rip off content, like recording Blu-rays and recording shows off of Netflix and that sort of thing. And so what that is it's just a content protection protocol that has keys that are stored on the IC. Generally speaking, only the manufacturer of the IC, who works closely with the HDMI Corporation, is privileged to have access to these keys when they bake in their chips on the newest revision. They probably even release a new set of keys with every new HDMI specification that comes out. In the past, those HDMI keys have been, or those HDCP keys have been leaked, and people were able to create some pretty cool pirate hardware because of those leaked keys, but they try to stay on top of it and release new revisions to prevent that from happening in the future. The reason why I'm bringing this up is because if you were to DIY or build on your own outside of working for somebody already in the industry, you would not be able to create a compliant device without first becoming an HDMI adopter, which also includes becoming an adopter of HDCP. So you would not be able to make a device that is fully compatible with all the frame rates, resolutions, and stuff like HDR that come on modern delivery formats, like those HDR Blu-rays and those 4K content delivery stuff. So you couldn't do it by yourself. You would probably have to be somewhere in the industry, or at least become an HDMI adopter if you're a sole proprietorship or something like that. But I would be remiss without mentioning HDCP if I'm talking about HDMI. So moving on, this is a soft and hard IP core, and what that means is if you're working in an FPGA development environment, you can download an entire intellectual property core that is a collection of the files with hardware description, with a description of an HDMI system, like that block diagram we saw here, basically coded in a hardware description language for the purpose of loading onto an FPGA so that you can work with transition minimized differential signaling for HDMI. And the soft IP core is the reason why they have these split up into two IPs here is I think the soft one could probably be used for DisplayPort as well. And then the hard one is whereas you finalize those signaling types for HDMI. And you might swap that hard IP there out for a different one if you were going to work with DisplayPort or some other video transport. And so that's an example of a block diagram there that would be the IP cores that would be implemented onto an FPGA. And that's essentially all I've got for this topic. It was, like I said, it was going to be a crash course in HDMI and TMDS. I had a lot of fun researching the topic, and there's still more I'm looking into. If you have any questions for me or you have any feedback, I would love to hear about it. If you're seeing this on YouTube, just drop me a comment below or just email me if you've got my university email address. I wanted to thank you guys for checking out my presentation, and I hope you enjoyed it. Thank you very much, and have a great day.